Okay, this question is about the generator effect, which is the opposite of the motor effect. So instead of producing movement, what we're going to do is we're going to generate a potential difference and therefore a current. So it says figure below shows a coil and a magnet. An ammeter is connected to the coil. So let's have a quick look, get our heads around what we're doing here. Let me just find my laser as well. So there's our ammeter. It's going to measure current if there's one flowing. There's our coil of wire, often known as a solenoid. And there is our magnet. Now down here I've drawn a little magnetic field around the magnet. I'm going to use that in a minute. The ammeter has a center zero scale, so it's zero in the middle, so it'll be positive over there, it'll be negative over there. So the values of current going in either direction through the coil can be measured. The teacher moves the magnet slowly towards the coil. So what I'm going to do now is I'm going to place this magnetic field around that magnet there, so it's about the same size. There you go. So that shows the magnetic field around the magnet. Go big, 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 go big, big. There it is, roughly. Okay, and I'm moving it slowly towards the coil, and it goes through the coil like this. So you can see the magnetic flux density of the magnet is starting to link with the coils, okay, or cut them if you like. So we call that flux cutting, okay, and it's when we've cut through those coils that we get an alternating potential difference. Or sorry, not alternating, just a potential difference generated, okay? Now, if we go back and forth, we get an alternating potential difference. And then we got generation, power generation in a power station. Anyway, explain why there's a reading on the ammeter. So this is what I want you to say. First of all here, let's go back to my laser. Oh, there it was. There's my laser. There is a magnetic field around the magnet. So all I'm doing is saying that we've got a magnetic field around the magnet. This magnetic field changes as it moves. So it's changing. As I move it through, the magnetic field changes and cuts through the coil, like I've just said. Or you could say links with the coil. Use that phrase, flux linkage. Therefore, so a potential difference is induced. Use the word induced. It's underlined because as an examiner, I'm looking for that word. I want to know that you know that we're inducing something. We're causing something to happen. So we're inducing a PD across the coil. And if there's a potential difference across this coil, then we've got a complete circuit and therefore current, it flows. So we get current induced in the coil. So that's what that one's all about. So I'll leave that for you to have a look at. That's the mark scheme. So in all these questions, as I go through them, I want you to realise that the same kind of thing comes up all the time. You'll often get questions on motor effect, where you're putting current in to a wire that's in a magnetic field, and then you've got the permanent magnet interacting with the magnetic field that's produced around the current carrying wire, and then you've got movement, and you're using Fleming's left-hand rule. So the generator effect is effectively the opposite of that. Then it says the table below shows some other actions taken by the teacher. Complete the table to show the effect of each action on the ammeter reading. So if I hold the magnet stationary and move the coil slowly towards the magnet, what happens to the ammeter reading? Well, what did we do in the first place? Let's go back. So that's moving the coil towards the magnet. What was the first situation? We moved the magnet towards the coil. So we could keep this still and move that towards that, or we could move this towards that. So it's basically doing the same thing. As long as you've got relative movement between the two things, then you're going to get a current produced or a current induced because you've got an induced potential difference. If you hold the magnet stationary, there's no energy going into the system. So if this is just stationary, let's say I move it over here and it just sits. Whoops, let me do that again. I just move it and it's not going to move. Why aren't you moving? Hang on a second. Pause, pause, pause. There it is. So it's just sitting there now. There is no movement, and therefore we've got no induced potential difference. You have to move this. Again, that's alternating. That's a nice steady current. If I move it faster, you're going to get a greater current. There's basically more energy going in the system, therefore you're getting more electricity out. Okay, it's all basically the transfer of energy. If we move the magnet quicker, we get more energy, or we get more induced current, is what we need to say. And then if we reverse the magnet and move it slowly towards the coil, we're going to get the same induced potential difference as at the start, but it's going to be in the other direction, okay? And then finally, the magnet moves so that there is a steady reading of 0.05 amps. So there's my current for 6 seconds. So my time is 6 seconds. So you should already be thinking, what's going to link current and time? Well, we're going to calculate charge. If you look on the formula sheet, you'll get Q equals I times T. So, and then we want the unit as well. So calculate the charge. The charge is going to be 6 multiplied by 6. That's nice and easy, isn't it? Yeah, 6 multiplied by 6. So that's, yeah. Oh, no, sorry, my mistake. So it's going to be the I, which is 0.05. So 6 basically times 0.05. 6 times 0.05, we're at 6 times 5, which is 30, so it's going to be 0.3. And the units are coulombs. And that's it, 13 marks.